Welcome to another video, and in this one we're going to be starting a series based on semiconductors. So later on we're going to be looking at transistors and integrated circuits, but to start with we're going to look at the simplest semiconductor of all, which is the diode. Now these come in a variety of forms, but they all have one overlying characteristic, which is that they are the electrical equivalent of the non-return valve. To illustrate that, before we start doing anything practical with diodes, let's have a look at the theory behind them. So let's get stuck into the theory then, and let's get it out of the way. And what we can see in front of us here is a drawing, and the drawing is of the internal construction of a diode. Now, as you can see, we have two substrates. We have a P and we have an N. The diode is usually made of germanium or silicon, the latter being the most common. And we'll dope the materials. For a P, we'll dope it with something like boron, and for an N, we'll dope it with something like phosphor. In that way we alter the chemical properties of the materials, and we can make them conduct in any way we wish, within certain limits of course. When we do that, we get a thing called a PN junction. PN junctions are present in lots of things. You can find them in transistors. If you put another N substrate there, you get an NPN transistor. If you put another P substrate there, you get a PNP transistor. And you also find them in solar cells, and it's hardly surprising because they're all semiconductors, and the diode is in fact the simplest form of semiconductor there is. Semiconductors are born out of the strange world of quantum physics, and we're not going to delve too deeply into that world because it gets very quickly theoretical, very quickly mathematical, very quickly confusing. And so what follows is a very simplified explanation of the way things work. In semiconductors, when we talk about the flow of current, we tend to think of it in terms of electrons and holes. And electrons move from the N substrate to the P substrate, and holes move from the P to the N. However, under certain conditions it won't do it at all, and under others it'll do it very quickly. So there are three ways to bias the diode, and we're going to look at all three in turn and what the practical upshot is for us. Now, you'll see a thing here represented by this grey stripe called a depletion layer, and that's theoretical there. It's the actual part where the P substrate meets the N substrate and they're put together. The depletion layer can seem to grow or shrink and vanish. And if we look at the ways to bias this thing, then we'll find out why. So the first thing we need to look at is the zero bias, and the zero bias is simply another way of saying that we're putting no voltage across the diode at all. And if we put no voltage across the diode, what happens is it's very difficult for the electrons and the holes to recombine, and so very little current comes out of this end. You might get something in the order of microamps, but it's very hard to detect and is of very little concern to us and of very little use to us. Following on from that, we can do a forward bias. Now if we have a DC supply and we make the anode face the positive of the DC supply and the cathode face the negative of the DC supply, what will happen is this depletion layer will seem to shrink and vanish. And it's not really the layer itself that's growing and shrinking. What's happening is we're imparting energy. And so the electrons and the holes find it much easier to cross the gap between the P and N substrates and recombine. And the more we can do it, the more current we'll get. We can also reverse bias. Now, a reverse bias is just as it sounds as well. We swap the terminals around. So we have the cathode facing the positive of the DC supply and the anode facing the negative of the DC supply. And what happens then is this depletion layer seems to grow. It doesn't really though. What's happening is all the electrons are clustering this end of the diode, and all the holes are clustering this end of the diode, and because they've got that much more distance to go to recombine, they don't, and we'll get no current. In this way, we can think of the diode as the electrical equivalent of the non-return valve. Well, let's have a look at something else on the same page, and it's a diagram from SparkFun, and it's a very good diagram. It shows us a lot of things on this diagram. I'll just zoom out so we can see it a little better. So, well, so on the y-axis we've got current, and on the x-axis we've got voltage. We're going to look at forward bias first. And as you can see, as we start putting voltage in, it doesn't do anything, but when we get to a certain point, it starts to conduct. And we don't need to go much further than that certain point before it conducts wildly and starts acting like a piece of wire rather than a resistor. Now, down here you can see the values, and these are the breakover voltages. So, silicon takes 0.7 volts before it starts to conduct, and so there we are. That would be the start of the conduction point for a silicon diode, and as you can see, it doesn't need to go much further than 0.7 before we get the current coming through. Germanium would be 0.3 volts, so if you imagine it, we're looking at a germanium one now. There we go, 0.3 volts. We don't need to go much further before the current starts to come through. However, in reverse bias, we can put a much bigger voltage in. Now, this point here, according to this diagram, is 50 volts, so we could say that's what, 35 or so, before we start to see the knee and current comes through. Now this is the fourth important term for the diode, and what we see here is a breakdown. So, in reverse bias, the diode will not conduct until it reaches a critical voltage. When it does reach that critical voltage, it goes through the knee, and when it gets to about there, it'll probably never recover and will permanently damage the diode and won't be able to use it again. As it reaches that critical voltage, it breaks down and lets current through just like an open wire. SparkFun have kindly supplied the symbol for a diode as well, and you can see the idea here. That's the anode, that's the cathode, and at the cathode there's a little bar. Current's not coming through this way, but it will go through that way. And that's really all the theory there is, or rather all the theory we're going to look at the moment. So let's do an experiment into preventing reverse polarity with a diode. And of course that raises the question, why should we want to prevent reverse polarity? Because of these things really. This is a DC barrel jack, and this one looks as though it's a standard 2.55mm. And what we have, if we look at it, is a hole here in the centre and a sleeve here in the outer, and the whole thing is separated by a piece of plastic to insulate it. Now, having two conductive pieces, you can wire it up so that the centre is the positive of the DC supply and the outer the negative, or the centre is the negative of the DC supply and the outer the positive, and we usually go by terms of centre, so we'd have centre positive or centre negative. And what this means is that when you plug something in, you can give it the wrong polarity. The device may require centre positive, or it may require centre negative. Some chips will release magic smoke and blow up if you give them the wrong polarity. And so, in many devices, you will find a diode to prevent reverse polarity. And the experiment we're going to do here is designed to illustrate that. So I have a power supply here, and I've got a positive rail and a negative rail. I also have a diode. We're going to ignore that for the time being, and what we're going to do is we're going to put in a motor. And it's a bog standard little toy motor. It's a DC motor. It has coils on the rotor and 2 permanent magnets on the stator. And if I plug it in to the positive rail and the other end to the negative rail, as you see, the motor starts to work. If I switch them over so that what was positive goes to negative and what was negative goes to positive, the motor spins again, but in the opposite direction. The same thing will happen if I switch around the terminals of the power supply. So it doesn't really bother the motor. However, most electronic devices are not like that. So let's put the power supply back as it should be. And now I'm going to put the red wire from the motor facing the cathode of the diode, and the motor starts to spin. What I'm going to do now is I'm going to turn the terminals around so that positive is where negative was and negative is where positive was, and absolutely nothing happens. However, if I turn the diode round, so what we can conclude there is that the diode is preventing current from flowing when the polarity is reversed. And this is how it works to prevent devices from being damaged. So for the next few minutes what we're going to be doing is looking at a process called rectification, and this is a particularly important thing in electronics. What we do is we take an alternating current or AC waveform and we turn it into a direct current or DC waveform. This is particularly important in all branches of electronics, and particularly so in computers. Computers are digital, and digital devices do not work with alternating current. If the logic level is 5 volts, the 5 volts will be there, or the 5 volts will not be there. There is no in between. And it's always a direct current. And so we need to look and see how we can achieve a direct current from an alternating waveform such as we get from a wall socket. To illustrate it, what we're trying to do is we're trying to take a waveform like this and turn it into one like this. Well, let's get stuck in and see how we're going to do it. So this is the circuit for our half-wave rectifier made on breadboard, and I don't think really we can grace it with the term circuit because there's not much to it. What we have is an AC power supply coming into this rail, and a diode coming out. We have a 4.7k resistor there to make a comparative load. From the end of the resistor it goes back to the supply rail, and between there and there what we should have is an AC supply modified into a sort of DC supply. We've also got a resistor here and an LED, but they're not doing anything yet. The reason for that is when we've done what we've got to do with the waveforms, we're going to see if this circuit will drive an LED. I have a test point here on the rail to put the voltage probe into. The voltage probe, I do apologise, I mean the oscilloscope probe into, to see what sort of voltage we're getting at that rail. And I have a junction here between the diode and the resistor, into which I'm going to put the oscilloscope probe after that to see what we're getting. So I'm going to swing the camera around and turn it towards the oscilloscope. I'm not a very good cameraman, so bear with me. This may not go very well at all. Well, that looks alright, so let's see what we've got. So, this is me putting the oscilloscope probe onto the voltage rail. Oops. And there we are, we've got an AC waveform, and if you look in the bottom right hand corner of the screen it tells you the voltage as well, and that says 13.62. Now that's me taking the probe off again, and this is me putting the probe on the junction of the diode and the resistor, and let's see what happens. Now look at that waveform, and I'm going to hold that, take the probe off and hold that, and we have a look at what we've got here. What we've got is a kind of DC waveform, because as you can see it's not dipping below that line, and what it's doing is it's taking the top of the AC waveform we saw before and largely ignoring the bottom of the AC waveform we saw before and staying flat. And the voltage is saying 7.71 volts, it's roughly half of what we had before, just a little bit more. So, we can see the flat there, we can see the crest there, and we can say that the half-wave rectifier is producing a half wave there and nothing there. And that's because, as we know, the diode will not conduct in reverse. So let's swing the camera back to the circuit as such as it is. And as said, let's see if this little rectifier has enough oomph to it to drive this LED. Apparently so. So we're continuing our experiments into the rectification properties of diodes here. What we've done this time is we've set from this AC output here, which is safely under a cover and leading out to here, a bridge rectifier. And the bridge rectifier is taking in the AC output through these yellow crocodile clips, because it's been set up to be breadboard friendly, and through these red and black ones here, it's putting out a DC supply. And to see what we've got, I've set up a multimeter and I've set up an oscilloscope. The load we've got here, if I zoom in a little bit, consists this time of only this resistor and this LED. So let's see if it works before we do anything else. Apparently so. So let's zoom out again. Now, I'm going to use the oscilloscope to show the waveform and the multimeter to show the voltages, because the oscilloscope will show us average voltages and it'll be confusing to work out, so I might as well just use a multimeter to see what we've got. So, if I put the multimeter probe here and here, it should show us what we've got in DC. Alright, well that's 10.69 volts. We've lost a couple of volts through the bridge rectifier, but I'm not too bothered about that. Let's have a look at the waveform, turn the camera around to see what the oscilloscope is doing. I don't know how clearly we're going to be able to see that. I'll try and focus the camera in a little bit more. Well, I hope you can see that. It's not very good in the viewfinder, but it is at least visible. So what we've got is a waveform that goes up, down, up, down, up, down, up, down, up, down, but it's never dipping below the line. So it's a direct current of a form. And it's what we'd expect to see from a bridge rectifier, and what it's actually doing is it's taking the AC waveform, and if you imagine that inverted, that would be exactly the same, but upside down, and it would be a perfect sine wave. So basically what we've got is a sine wave where this bit here has been inverted to form this bit here, and then this bit is normal, and then this bit here should be there, and it's been inverted to form this bit here, and so on throughout the entire wave. Excuse me. Now, as a DC supply, that's, you know, still alright, and sometimes we can make use of those. In telecommunications we make use of that sort of thing all the time, and we pick up a signal on the rising edge. So, in electronics though, what we want is something that looks a bit more like a battery output, and the way we're going to do that is we're going to put a smoothing capacitor parallel to the supply, and this is an electrolytic capacitor, 470 microfarads, and it's able to deal with 16 volts. I would have liked to have used one that can deal with 25 volts just for safety's sake, but 16 volts is okay here, and I haven't got one at 25 volts, so let's just place him in there. You might have seen a slight change in the LED there, because what's now happening to the waveform, zoom out a little bit, is it's up there and it's a nice straight line. And if you remember the illustrations I put forward first, that is exactly what we wanted. So that's it. And what we built there is an AC to DC rectification circuit. So what we looked at previously is how to regulate an incoming voltage in its waveform, and we've seen that we can use a barrier or a Schottky diode to turn an AC waveform into a DC. What we're going to do here is we're going to use a thing called a Zener diode, or you might possibly hear Zener, that's the American way to pronounce it, to turn a DC supply of a given voltage into another DC supply of a different voltage, and the voltage that it turns into depends on the voltage for the Zener diode. And this is the thing here. It's very, very tiny, and what we're going to do is we're going to zoom out a little bit, and we've got a multimeter here, and hopefully when I switch it on you'll be able to see the digits. Now if I check the supply coming in like this, we'll see it's not far short of 9 volts. Let me move the multimeter this way a little bit because it doesn't seem to be in the viewfinder very much. Try that again. There we are, we'll see it's not far short of 9 volts. A little bit, tiny little bit off. However, if I put this probe at the junction here, we should get about 5 volts, or more probably 5.1. And that's what this diode is doing. It's regulating a 9 volt supply and taking it down to 5.1. And what I'm going to do is I'm going to take the incoming supply and I'm going to turn it down so that it's actually 7.5 volts. Bear with me a second, there we are. And let's just check and see what we have. Now we've got about 7.5 volts coming in, and if we check what's at this junction here, you can see that it's hardly affected it. I'm going to try and take it down to 6 volts and see what happens. I think that the diode will probably drop out at 6 volts, but let's have a look. Let's make sure we've got 6 volts there. Just slightly over, and let's see what we get here. Didn't drop out. Well, it's soldiering on. So we've had 3 different incoming voltages, and the difference between them has been about 3 volts. But the outgoing voltage from the Zener diode has always been from 5.11 to 5.15, so we get a remarkably stable voltage there. Zooming in a little on this, you can probably see that the diode has been put in series with a resistor, and we're going to look at that. There is some theory and some mathematics behind that, and so let's get stuck in and see what that's all about. So onto the theory we've got to do behind it now, and you can see on the screen here there is a data sheet. And the data sheet is for the BZX79C2V0 through BZX79C75. And those numbers actually mean something. The Zener diode that I used in the example that we've just seen gloried in the name of the BZX79C5V1. Well, the BZX part means that it is a Zener diode. The 79C part is the type and gives you a clue as to how much power it can pass. And the 2V0 and 75 at the end there give you a clue as to the output voltage. It would be 2.0 volts and 75 volts in that case. The one I used, of course, the BZX79C 5V1. The output voltage is 5.1 volts, providing you've got the series resistor right. Now we look down a bit, and this part tells us how to choose the series resistor, or at least it gives us information to help us choose the series resistor, as we're looking at the electrical characteristics, and importantly we're looking at the power dissipation, which is right at the top there. So the power dissipation is given a value of 500 milliwatts, and as we know, 500 milliwatts is exactly the same as half a watt, and that helps us with the maths we've got to do to get that series resistor. So let's boot up Mr. Calculator to give us a helping hand here, because it's Saturday evening. And okay, so we've got I Z max equals WZ over VZ. Now we see Z, that's to do with the Zener diode, and I max, of course, is the maximum current. And the maximum current will be the wattage it can handle over the voltage it outputs. So we can put some numbers in there. We know that it can handle 0.5 watts. And we want to put that over its output voltage, which is 5.1. I said Saturday evening, and I can't bother to do that in my head, so 0.5 over 5.1. And we might as well call that 0.01. And that is, of course, in amps. So, knowing IZ max, we can now find RS, which is the series resistor. VS minus VZ is, of course, the supply voltage minus the output voltage from the Zener diode, and we know the supply voltage is 9, and we know that the output is 5.1, so we got 3.9. 3.9 over 0.5, sorry, 0.01, don't know what I was thinking there, equals 3.9 over 0.01, 390. And that is, of course, in ohms. And that's the value of our series resistor. Now, 390 ohms is not standard, and I'm using very, very crude E6s. So it's not even near a standard for E6. I could either go 330, in which case I stand a bit of a chance of blowing up the Zener diode, or I can go to the next one, which is 470, and take the current down a little bit. Now I'd rather do that because if I take the current down a little bit, I can always compensate for that by putting some sort of transistor stage at the output if I need it. However, if I'm only supplying a reference voltage, a current like that won't matter. All I'm going to be doing is feeding the voltage to a microcontroller, which doesn't need much at all to set it off. So we can be happy with that, and we can put the 470 ohm resistor in there and get a 5.1 volt output, just as we saw. And we'll finish off talking about Zener diodes then by looking at another excerpt from the datasheet, which is the characteristics of it. And here we have the symbols. This one at the top here is not seen very often. It's the normal symbol for a diode, but it's got a little stick pointing off the bar on the cathode, makes it a little L shape. This is the normal one, which you see almost everywhere, and it's much more intuitive because at the cathode it actually has a little Z, and you can't possibly mistake that. So you know exactly what that is. That's a Z in a diode. This graph we've seen before, and as you see, if we forward bias it, it works exactly the same way as any other diode, the barriers and Schottky's that we've already looked at. But it's in the reverse bias that we're interested, because it does something with a little bit of a twist. As we approach the minimum current for conduction, we experience a thing called an avalanche breakdown, and this is what the Zener diode is designed to do. When it gets to the avalanche breakdown, it starts to conduct a voltage over there which is almost constant. And I say almost because, as we saw in the preceding example, if we put the voltage supplied down to 6 volts, then we got 5.11, and up to 9 volts, then we got to 5.15. Now that is such a narrow range of output for such a widely fluctuating range of input, it can be considered constant. And this leg here represents that. As long as you don't go over the maximum current, you will get a very, very narrow band that the output voltage can be at. And in the case of my BZX79C 5V1, that was 5.1 volt. So in this penultimate section of this video, what we're going to do is we're going to look at a thing that everybody sees every day, whether they know what they're looking at or not, and that is the light emitting diode, or LED. And as you can see, I've got a selection of them here we're going to have a quick look at, and I've also got a little apparatus here on a breadboard set up so we can see what they do. And if I zoom in on the apparatus, you'll see that what I've got is I've got a DC supply with a positive end, a negative end, and a resistor. The resistor here is 540 ohms, and as you get a bit older and a bit more experience with these things, you start to find shortcuts, and my shortcut is that with 5mm LEDs and on 9 volts or less, I can use a 540 ohm resistor for any LED and it will work properly. And if I want it to be a bit brighter, I use a 330. There is a mathematical formula that tells us the exact resistance for any LED, and we'll look at that later when we come to the theory bit in a few minutes. But for now, if I zoom out again, and what we're going to do is we're just going to put a few LEDs in and see what happens. We'll start with this one. Now, this is a standard 5mm, and as you can see, it's got a red coloured cap, and we'd expect that to shine red. I'm not going to harp on about the colour of the cap just for the moment, because I'll do a little bit about that later. But what we do need to realise is that one leg is longer than the other on these through-hole resistors, on these through-hole diodes. The long leg is the anode, and that needs to face positive, and the short leg is the cathode, and that needs to face negative. In addition, the resistor must be between the positive and the negative. And I'm going to say a few words about that in a minute as well, but first we'll put the diode in and see what happens. And there we are, it glows nice and redly. If I turn it round, it does nothing. If I turn it back the right way, it glows nice and redly. And like any diode, if you put it in reverse bias, it won't conduct any current, or it won't shine. So, there are three schools of thought on the forward resistor here. The first school of thought states that you have to put it on the anode. The second school of thought states that you have to put it on the cathode. And the third school of thought, which is the one to which I subscribe, says that it doesn't actually matter unless you want to do something with the junctions, so put it either way. The forward resistor is in there to stop the LED blowing itself up. What will happen is that the LED will, if you put it to positive without a resistor, and then at the other end negative, galump as much current as the supply can handle, and it will very, very quickly burn itself out. That is the only reason we need a forward resistor, and in fact, under certain circumstances, if you're using 3 volts and a 5mm LED, you can get away without a forward resistor, though it's not a recommended practice. Well, having said that, we've seen a red LED. Let's have a look at a few other colours. Red LEDs were for a long time the only LEDs you could get, but nowadays you can get yellow ones, whoops, and green ones, and they're the standard ones. They're the cheap, standard, non-expensive kind. If we move on a little bit here, you'll notice I've got one here that has no colour on its cap. It's just clear. What happens when I plug it in? It shines bluely. Here's another one with no colour on its cap. It's very clear. What happens when I plug it in? It shines whitely. So with the red one back in, what we need to do is we need to find out why these LEDs have so many different colours, and a lot of people say that it's to do with the colour on the cap, but we've just seen that 2 clear ones shine 2 different colours, and so, you know, that leads to 2 questions. Either they could all be white and they have a different colour cap to diffuse the colour, or there's something in the compounds that that shine different colours. So, what we're going to do is we're going to spend a couple of minutes looking at colour theories and wavelengths of light, and then we'll come back and see what's going on. Well, in front of us now we have a guide to the wavelengths of light, and light is debatably a particle or a wave. And here's a bit of history. Isaac Newton is one of the greatest physicists that's ever lived, and he believed that light came as a stream of particles. He called them corpuscles. James Clerk Maxwell is another one of the greatest physicists that ever lived, and if you go to Edinburgh he's got a huge statue on Great George Street to prove it, and he said that light is actually an electromagnetic wave. A bit later on you got people like Max Planck and Albert Einstein who said that light does exhibit the characteristics of a wave, but it also exhibits the characteristics of a particle. And experiments like the Young slit experiment proved that that was the case, and the fact that light is both a wave and a particle, or behaves as both a wave and a particle, is a cornerstone of modern physics these days. But we don't care about that very much. What we care about here is the wavelengths, and the wavelengths are what hit our eyes. the wavelength that's hitting our eyes is 700 nanometers, we'll see red. If it's 400 nanometers, we'll see the violetty purple bits at the other end. And similarly, if it's 550, we'll see green, 500 or so, we'll see bluey, and 650 or so, we'll see orangey. Now, all of this has to do with the way that LEDs are constructed. So, back to our apparatus, and let's see what we've got. So, the red LED. Now, when we looked at the barrier and the Schottky and the Zener diodes, what we found was that we had a PN junction. And we doped the PN junctions with things like boron, antimony, phosphorus, and made them do the conduction like that. With an LED, we use slightly more exotic materials. We still have a PN junction, it still works as a normal diode, but the materials are different. So, this is a red one, and this uses gallium, which is number 31 in the periodic table, phosphorus, which is number 15 in the periodic table, and the material which is number 33 in the periodic table, which is, in fact, arsenic. So, don't be eating very many of these. Let's change the colour. And we're going for yellow. Now, this also uses gallium, arsenic and phosphorus, but it mixes the ratios around a bit. And by mixing the ratios around a bit, what you'll get is a gradual shift from 700 nanometers or so down to around 600. Let's change the colour. Green, I think. Oops. If I don't drop it. Now, green is a little more exotic, and it gets rid of the arsenic, you'll be pleased to know. And in green, the common ones are aluminium, gallium, and phosphorus. And when you do that, you end up with a light that shines in the 550 to 570 nanometer range. Change the colour again. Blue, there are two common ones for blue. There is silicon carbide, which I know absolutely nothing about chemically, and there is zinc selenide, which I'm equally ignorant about chemically. They're very exotic, and it's the reason why blue LEDs tend to be much more expensive than the red, yellow and green ones. And finally, white again. Now, white is really very bright blue. It's at the 450 nanometer, and that is actually blue. But what they do is they make it so bright that it looks white. You will see a hint of blue if you put your eye to the top of it, but it's not recommended that you put your eye to the top of it because it can hurt quite a lot if it's bright enough. However, a white LED like this in a smaller form is used in torches. It's very irritating to some people because it makes a very harsh light. Chemically, it's gallium nitride. So, We've used the standard through-hole 5mm LEDs to look at the colours and look at the chemical composition so far, but they don't just come in that format, they come in quite a lot of other formats, and here's one of them. This is a side-looking LED, and the idea is that you can mount it onto a panel and have it shining down onto a sign or a piece of paper or anything you want to draw attention to, really. This is part of a job lot I bought. If I hold it up to the camera a little more, you might be able to see the difference. The format is, it's in an arrow. And I bought these to use on a push display, so the arrow pointed to the buttons I wanted people to press. Now this is another through-hole one. It's a 3mm LED. It's exactly the same as a 5mm LED, but a lot smaller, and it's used for very small devices. There's some on my power supplies, and there's one on my tablet computer that is exactly the same as this, and they're designed for smaller devices, and they use a lot less power than the 5mm LEDs. This is a flat bar. You can see the profile there is a rectangle, and the light shines up there and comes through the rectangle, and basically what you use these for, you can use them for those graphs you see on sound bars where the view meter is going up. So you can have one there, one there, one there, one there, and the louder the sound, the more of these are lit. This one is one we're going to be looking at later, and it's interesting because it's, let me just focus the camera a bit more there, sorry about that, and it's interesting because it's 3 LEDs in one. So basically this will shine red, green and blue, or any colour that is a mixture thereof. And you can actually get thousands, if not millions, of colours out of this if you're careful enough with it. And then we have this one, which is quite an expensive thing, and this is one used in the telecommunications industry. And basically what you do is you can put a waveguide on there, and you can send signals without wires, signals by light. You can modulate how quickly the LEDs switch on and off. So, as I promised, we'll have a look at the forward resistor, and then we'll get on to a little bit more theory, and we'll look at a practical circuit. Now I use a 540 ohm resistor here, and you can see that the LED shines quite brightly, quite nicely. But I'm going to take the 540 ohm resistor out, and I'm going to put in a resistor that is a bit too small, and let's see what the difference is. The LED is shining madly there, that's brilliantly light, and what will happen if I let it do that for too long is that the life of the LED will be very, very much shortened. It will burn hotly and brightly, and eventually it will blow itself up. And that's why it's important to get the resistor right. Well, let's have a look and see how we do that. So what we have in front of us now is an equation, and it's the equation for finding out the actual resistor we should use properly with an LED rather than taking shortcuts like I do. So the resistance in series, i.e. the forward resistor, is equal to the value of the voltage supplied minus the value of the forward voltage of the LED divided by the forward current of the LED. Now, that looks a bit like gobbledygook if you don't know what a forward voltage and a forward current of the LED are. So let's scroll down a bit to a nice friendly graph which will explain things. And as you can see, we've got 7 different types of LED on there. We've got the infrared, we've got the red, we've got the amber, we've got the yellow, green, blue, white. Up the y-axis here, we've got the forward current. And across the x-axis here, we've got the forward voltage. And as you can see, the different kinds of LED require a different kind of forward voltage to kick them into action. If you don't give them that forward voltage, they won't do anything. And blue and white require a larger forward voltage than does red and infrared. Now, the IET publishes a table, and it gives the average forward voltages for all these kinds of LED, and it says that an infrared LED requires a forward voltage of 1.2 volts, and a red 1.8, amber 2, yellow 2.2, green 3.5, blue 3.6, and white 4. And it's all due to the type of doping and the ratios of the doping and how the internal workings of the LED is constructed, and the table that I've just quoted seems to chime with this graph. So what we'll do is we'll go back to the maths in a moment and have a look. But before we do that, we need to know the forward current. Now, it's a fairly safe bet that the forward current of any LED, if it's going to shine the correct brightness, is going to be around 20 milliamps, and that's why this dotted line is here. So, assume then, unless you are told otherwise, that 20 milliamp is the forward current of any LED. So back to the equation then. Now, as I've said, I habitually use 540 and 330 ohm resistors to run my LEDs because they tend to run a bit dimmer than normal, and they're not quite so bright and not quite so irritating to the human eye. However, there are occasions when we do need to work out how brightly we can run the LED at maximum, and this is going to help us. So, forward resistor equals supply voltage minus forward voltage all over the forward current. Now, if we assume the supply voltage to be 5 volts, which is standard logic voltage, that seems a fair enough thing, so we can start sticking some numbers in. Let's say we're going to run a red LED, which is 1.8 volts on the forward voltage, so we'll have 5 minus 1.8, and that gives us 3.2. Let's stick that number in there, over the forward current of the red LED, and we're assuming that to be 20 milliamps, which is 0.02. There's a Mr. Calculator on the job here. 3.2 over 0.02, 160. So there we go, we have 160 ohms. As I said before, that will run the LED at its perfect brightness to conserve it, and it will be irritatingly bright to the human eye, but sometimes that's just what we need. Let's say we're going to make a torch. To make a torch, we'd be using a white LED. And let's say our supply voltage is 9 volts. Now, the forward voltage of a white LED is 4 volts. So we've got 9 minus 4, and that gives us 5, so we can stick that number in there. And we're going to assume the same forward current. So we'll get Mr. Calculator on the job again. 5 divided by 0.02, and there we are, 250 ohms. And the takeaway from this is that the larger that is, the more likely you are to have a larger resistor. The larger that is, the more likely you are to have a smaller resistor. And that about wraps it up for the theory side of this. So what we'll do next is we'll have a look at a practical circuit involving an infrared emitting LED and a diode that picks up infrared and will make a little beam break alarm. There's a little wiring diagram of what I intend to do here, and as you can see I'm using a microcontroller. Don't really need to, but it makes it much easier than using discrete components for the rest of the circuit. For our purposes, what we're interested in is these two things here. So we have an infrared emitter, and basically that is an LED, and it's been put onto a breakout board to make it more breadboard friendly. The infrared LED takes 1.2 volts forward and is made of gallium and arsenic. On the other side we have a diode which has also been built into a breakout board, and it has some concomitant circuitry. It has automatic gain control and preamplifiers and things like that, and what it does is the diode looks at the infrared, and if there's a signal from infrared it goes active low, and it sends a signal to the microcontroller and other things happen. Now, important things here are the forward resistors, and for the infrared emitter we have a 220 ohm resistor, and for the LED here, which is going to work as a signal to tell us that something has interrupted the beam here, it's a 680 on here, and that makes it quite dim and not so annoyingly bright. So let's see the thing made manifest and see what happens. This is the device knocked up on a couple of breadboards, and what we have here is, if we zoom in a little, not that far, we have the infrared emitter, and we have the diode that receives the infrared in a TSOP 18 package. And it doesn't look as though it's doing a great deal at the moment, and that's because we can't actually see infrared. It's above the 700 nanometer range that we saw earlier. But if we do something like this, and again, and you'll see that as any object moves between the beam and then moves out of it, and the alarm sounds. And you'd find things like this commonly in shops. They're used for counting people going in and out of the shops, and also in industrial premises. As the thing is coming along the conveyor belt, it interrupts the beam, and as it leaves the beam, and they can count how many packages have gone along that conveyor belt in a given time. So that's one application of a light emitting diode, and also an application of a photo receiving diode. And what we're going to do now is we're going to have a look at another application which is very, very handy and can be used to check polarities. So on the screen now then we have the schematic for a polarity checker, and I can't think of a device that's so useful but so simple and illustrates so many topics of what I've just been talking about as far as LEDs are concerned. And what we have is two LEDs, and if we say the red one for negative polarity and a green one for positive polarity, what we can see is that we have two resistors, each attached to to one LED. And one LED is forward biased and one LED is reverse biased. We have a voltage source here, and if the voltage source is coming through the right way, i.e. we have a positive polarity when we want to, what will happen is this LED, being forward biased, will shine, whereas this LED, being reverse biased, will stay dark. If the polarity comes the other way, of course, what will happen then is that this LED, being reverse biased, will stay dark, and this LED, being forward biased, will shine. And it's a good last little project for this video because it illustrates the thing I said right at the very beginning, about an hour ago, which is that the LED, or any diode in fact, is the electrical equivalent of the non-return valve. And it also illustrates what I said a few minutes ago about it doesn't really matter where the forward resistor goes. As you can see, it's on the anode on one and the cathode on the other. So let's have a look at the device made manifest and see what happens. And what we have here then is the thing knocked up on a breadboard. As you can see, I've done my usual shortcut with the 540 ohm resistors, and we have a red LED and a green LED. Let's see what happens when we give it 3 volts. And the green LED lights. If we swap the terminals over, which is akin to swapping the polarity over, only the red LED lights. I'll swap them back. And the red LED stays dark and the green LED lights again. Now, this is an example of why using the mathematical formulae is a guideline rather than a gospel. Because by using these 540Rs, I can make this measure any voltage I like. At the moment this is measuring 3 volts. Let's change the voltage. I'm going to shove the power supply all the way up to 12 volts and we'll see that the LED shines a bit more brightly. And if I change over again, and that would help if I put this terminal in the right place, so does the red LED. And the 540Rs are limiting the current, whatever the voltage, and it will do between 3 and 15 volts, and that's as far as I've tested it. It'll probably go up to 18, possibly even 24, but I can't guarantee that, I haven't tested it, thanks to these 540 ohm resistors, rather than the 160 or 200 or whatever we'd put in if we were following the mathematical guidelines religiously. So there we are. And that wraps up this practical section, and we can close the video with a few last words on the subject now. So we spent the last hour and a quarter or so looking at diodes, and we've done barrier, Zener and LEDs in some depth, and we touched on a couple of others as well. And there are a number of points that you should remember from this video, and the first is rectification. Then there are series resistors, and the two important terms, forward bias and reverse bias, and these will be included and studied in your handouts. And that's the end of the video. Thank you for watching.